Hello, this is question 3 from the 2022 MAT. We're going to start off by sketching y equals x squared minus 1 all to the power of n. N is 2 and n is 3 on the same axes, labelling any points that lie on both curves or that lie on the x-axis or y-axis. Okay, so the things we're drawing out, get a closer look. So x squared minus 1 all squared, x squared minus 1 cubed. Okay, so positive powers, but we can get a negative number in the second one at least, so I will draw negative on the y-axis. So for the first one then, when x is 0 we're getting 1. It's going through here, we're symmetrical about the y-axis. When x is 1 we got a double root, and when x is minus 1 we got a double root, so we just need to have that going over there. Minimum, we'll have a maximum here because it's all got to be symmetrical, come around there and then go off over there. So that is that one drawn. Then for the second one, when x is 0 we're now getting minus 1, so that's at minus 1. We've got the same roots at minus 1 and 1, so how is this changing? Well, we've still got symmetry, so it's going to come round here and it's going to come round here. So when we get past that point, when are these two things going to intersect with each other? They're going to intersect when x squared minus 1 equals 1. So plus or minus root 2 for x. So that's where we're getting intersection points. So we've got one intersection point, but when it is root 2, we're getting 2 minus 1 all squared, so 1. So we're going to have an intersection point there, and we're going to have an intersection point there. So it's going to be going that way and then up, and then that way and then up. So we know the blue line's got to end up above the red line when x is enormous. And we can also see, I suppose, when x is between, well, when the contents of the bracket is between 0 and 1, then we're getting something between 0 and 1 squared versus something between 0 and 1 cubed. So the blue line is going to be lower, and then it's going to go higher when we pass through that point of root 2, 1 and minus root 2, 1. So that's sketched them and marked all the points on. Okay, it's quite a long first part to this question. Part 2, without calculating the integral explicitly, explain why there is no positive value of a, such as that integral from 0 to a is equal to 0 when n is even. Okay, right, so as in the red line and variance of it. So for n is even, then we can say that x squared minus 1 to the n is always greater than or equal to 0. So that means, so when we're going from 0 to a, so let's also say and x squared minus 1 to the n is greater than 0 for x is equal to 0. So we've got our lower limit of the integral being above 0, and the function itself never drops below 0, so the integral cannot be equal to 0. 0 to a, x squared minus 1 to the n dx must be greater than 0. Right, so that's that one. A bit quicker than the first part. Then if n greater than 0 is odd, we'll write that n is 2n minus 1, define am greater than 0 to be the positive real number that satisfies that. Right, so we've got the same integral, but this time it can equal 0, because at least if we've got an odd m, we've got some negative area down there. Explain why a number am exists for each whole number m greater than or equal to 1, so each odd n. Right, so more or less saying the same sort of thing but backwards here from compared to the previous part. For n is odd, then we've got the integral from 0 to 1 of all of that stuff dx is, well, actually I was going to say equal, is less than 0, and the integral from 1 to am is greater than 0. So eventually they've got to be equal in magnitude. Increase AM until the two integrals are equal in magnitude. Therefore, the integral from 0 at AM is equal to 0. Okay, right, new sheet. Find A1. Right, A1. That's going to be quite an easy one to do, I would imagine, because we don't have very many powers to deal with. So 0 to A1, x squared minus 1, and that's for m, so it's just all that to the power of 1. M is 1 is equal to 0. So x cubed over 3 minus x, A1 to 0. The 0 doesn't matter. We can divide through by the A1 because we know it's not 0. So we're getting A squared is equal to 3. So A1 is root 3 because again it's got to be the positive solution. Prove that A2 lies between the square root of 2 and the square root of 3. Okay. Right, this is going to be a fairly unpleasant looking integral then, isn't it? So 0 to A2. So that is for x squared minus 1. That would then be cubed dx. Right, so what are we getting on all of that? So that would be an x to the 6, so x to the 7 over 7. Then we'll have a minus 3x to the 4, so minus 3/5 x to the 5. We'd have a 3x squared, so that would be an x cubed. And we'll have a minus 1, so minus x. 0 to A2. Okay, well, again, the 0 isn't going to make any difference. So we want that to be equal to 0. Right, that's going to be a bit of a mess, isn't it? But we want it to be, we're saying that the solution is between root 2 and root 3. So we must be getting a negative answer for root 2 and a positive answer for root 3. So we want root 2. So let's sub root 2 should give us negative, and sub root 3 should give us positive. So, well, I can divide through by one of them. So we'll have root 2 to the power of 6. So that's 8 divided by 7. Then we're going to have 3 times 4 over 5, so 12 over 5. Then I'm going to have 2 and take off 1. So that is 1 1/7 plus 1, so 2 1/7 minus 2 2/5. So that's certainly less than 0, so that's fine. That's for putting root 2 in. Then we put root 3 in. So I'm going to get 27 over 7. Then it's going to be 3 times 9, 27 over 5, plus 3 minus 1. Right, so that is slightly more annoying that we got on this. So what have I got there for 27? So that is 3 6/7 plus 2, so 5 6/7 minus 5 2/5. So that is greater than 0, and happy days. Last part of the question. Without calculating any further integrals, find the approximate value of AM when m is a very large positive whole number. You may use without proof the fact that the integral from 0 to root 2 of that is less than 0 for any sufficiently large whole number. Right, let's go back to the sketch. I think that's going to help on this. So go back to the sketch. So they've given us up to root 2. So they said whenever we integrate from here up to here, we're getting something negative. So we've got some relatively small negative number. And we're making, what are we doing? We're making this bigger and bigger and bigger. We're increasing this power. So we're steepening this part of the curve. Okay, so it's going to be cancelling out the negative value faster and faster. Right, okay, so how am I gonna, maybe I want a new sheet for this. Right, so as we see from the graph in part 1, we've got that the integral from root 2 to am of all of that stuff dx grows quickly as m increases. Now we're making that gradient faster and faster and faster. Steeper, not faster. I've just had faster in my mind because I really want to say quickly in here. So yeah, maybe I'll just leave it as grows. I mean, it does grow. So the integral from 0 to root 2 is small and negative. Therefore, as m increases, the integral from root 2 to am will cancel out the integral from 0 to root 2 quicker and quicker. So therefore, as m increases, am will tend to root 2. I mean, it will never get there, but that's where it's tending towards. So that's a reasonable approximate value. Okay, there we go. That was a fairly swift question, quite a nice range of stuff. But I think that one was fairly manageable compared to some of the ones we've had before. Not a bad one, that. So again, not trivial, but not too bad.